All right, we just finished talking about horizontal and vertical asymptotes. Now we want to look at the slant asymptote. And I'm not sure how you were taught or whether you did see it at all in the grade 12, the 4U course. It does come up from time to time, so you need to be aware of it. So when does it happen, or when do you run into a slant asymptote? Well, it occurs when the number in a function has a higher, the numerator in a function has a higher degree than the denominator. So when you have a quadratic function, like I have here, over a linear function, what will happen is you'll do the horizontal asymptote test. So that's the first thing I always do. So right here, you can see where I did the horizontal asymptote test. Okay, so you do the horizontal asymptote test, and what you'll find is that your answer is undefined, 1 divided by 0. So what that tells you is that there's no horizontal asymptote. All right, so that's a bad thing, because that means then there has to be that means that there will be a slant asymptote. And how do we do that? We do long division. All right, so going back to how you did it in the 4U course, you basically take your denominator, and using long division, you divide your numerator to get the equation of your slant asymptote. All right. If you're uncomfortable, haven't done that or seen that, I can give you a couple of examples to work your way through. Okay, but the slant asymptote does come up from time to time. So you can see for this one, we do the long division, and I'll just step you through quick with it. So again, I need to multiply that term to make it an x squared. So that means I had to multiply by x. So when you do the subtraction, the x squared disappears. We bring the x down. Now I have an x. It's got to become an x. So here it is. So what do I have to multiply by? I multiplied by 1. So 1 times x will help me cancel out those x's. I have a remainder. Now I'm down to a numeric remainder. So it's impossible for me to make this 1 into an x using multiplication. So that's how you know you're done. So that results in the equation of the slant asymptote. So y equals x plus 1, and that'll be your slant asymptote right there. All right. So again, if you didn't see it last semester, let me know, and I can provide you with a couple of examples to practice with. Here's something that a lot of people get confused. Okay, a graph can cross both a horizontal and a slant asymptote. Okay, that doesn't help at all. So the graph can cross it. Okay, you cannot cross a vertical asymptote ever, but you can cross horizontal and slant asymptotes. All right, so absolutely cannot cross a vertical asymptote. So for rational functions, I don't know whether you came up with this little summary chart. I know when I taught the course, we came up with this little summary, and it says that if the top exponents, so the n and m are the exponents on the leading exponents on the numerator denominator. If n is greater than m, it's a slant asymptote. If they're equal to each other, there will be a horizontal asymptote at a divided by b. And if n is smaller than m, then the horizontal asymptote occurs at y equals 0. So that is more as a reference. So now, when you take, for the two situations below, okay, these two situations here, analyzing the limit as it goes to infinity will take care of this. So you don't have to have those, you don't really need this chart anymore if that's how you learned it in the 4U course. All right, if you do the limit, all right, it will automatically tell you where your horizontal asymptote is. Okay, it's that slant asymptote and the process involved in finding it that causes the trouble. End behavior. So this is what the graph does when it is leaving your 10 by 10 grid. Okay, so what does the graph, what's it look like it's doing? Well, how do we do that? In order to determine the end behavior, we analyze a value using our one-sided limits. So in this case, we're actually analyzing the end behavior, and end behavior refers to this. How does the graph act near the asymptotes? So I know I said off the end of the graph. Sorry, I meant as it approaches an asymptote. So we know that at +2 here, there's an asymptote. So we want to know the end behavior. So we do the one-sided limit analysis. So here's the function I have sketched. All right. So we want to look at the limit as it approaches from either side. So as we approach from the negative side of 2, so for example, that would be a 1. When you plug 1 into that equation, you end up with -1. So that means your values are negative, and they're going to become more and more negative. So as it approaches from the negative side, it's heading toward -infinity. As we analyze, so this is like the last unit, as it approaches from the positive side, so let's say we put a 3 in for the x, 3 take away 2 would be +1, so it's becoming more positive, so it's actually heading upward. Okay, so you use one-sided limits. So again, everything that we talked about in Unit 3, we're kind of throwing all into this graphing process. So you definitely want this to be outlined on your cheat sheet on how to graph a function with the rules that we talked about for derivatives. Okay, I talked about in the first video about what happens when the function is equal to 0. So for people that did not talk about this in the previous course, what is an inflection point? And it occurs when we have a change in concavity. So now I got people saying, well, that's no good because I don't have a clue what concavity is. Concavity is basically forming a cup. So it's the direction of the curvature. So this is called concave up. It forms a cup, okay, something you can fill. So that's concave up. Concave down is when the water falls out of the cup, okay, or previous classes said we talked about it looks like a frown. Okay, so an inflection point, when I'm looking right here now, my inflection point is when you go from a frown to a smile, or an upside down cup to a right side cup. Inflection point is the point where curvature changes, okay, when concavity changes from up to down. All right, we have a smile changing to a frown, so that point right there is your inflection point to change. And it occurs when y double prime is equal to 0. So if I were you, when you're making your cheat sheet, include it all back in that note earlier, or in that part of the note. So if it's greater than 0, it's a minimum. If it's less than 0, it's a maximum. If it's equal to 0, it's an inflection point. It's an IP. So it just saves you space on your cheat sheet. And inflection points are also known as critical values. So critical values are key values on the graph. So we have our XY intercepts are critical values, locations of max mins, inflection points, all fall in that category. So there is your inflection points. Now I do talk about concavity here in the final slide. Concavity basically determines the curvature of a function. So I just talked about that specifically. Here we have concave up. Here we have concave down. All right. If we have concave up, it occurs when the second derivative is greater than 0. When the second derivative is greater than 0. So that would be from point A to B, second derivative is greater than 0. So I believe in your 4U course, you ended up creating a chart with all the components in it. And I show you when I do the graphing process, I set up a chart myself that will analyze these values. But the chart value will help you determine when this is true. Okay, so basically at this point, just remember that when a second derivative is greater than 0, you have concave up. Concave down is when the second derivative is negative. All right. So what we're going to do is we're going to set up our ranges here. So this is where it's a little confusing with vectors, because we can set up ranges using the square brackets. So it says from -infinity to point A. All right, so -infinity to point A is this region right here. All right, in that region we have concave down. Our second derivative will be less than 0. And all we do is we just check a point in that region. All right, but I have a nice a nice little chart for you to follow through, and it makes it easier for you to follow, especially when you get into rational functions. All right. So we're going to talk about that, and you're going to see a bunch of examples because the next lesson is actually the graphing component or graphing examples. This is just getting down the terminology and basically constructing part of your cheat sheet so that when you go into the next section of homework, you know this is just talking about finding these particular values. So that's the end of lesson 39 here, the first lesson in this unit. The homework will follow in the next unit. There's no homework tied to this. It's just getting these concepts down.